Can you explain in one sentence what sustainable chemistry is?
Sustainable chemistry is about how chemistry can contribute to sustainability. So in fact, it's much more than green chemistry.
And can you say in one sentence what green chemistry is?
Yeah, green chemistry is about synthesis of chemicals or manufacturing of products sometimes, processes synthesis, doing with less energy, doing with less waste, and using renewable resources.
And do you think already Friedrich Wöhler thought about sustainability? I mean, the term didn't exist then, but...
I could imagine in terms of, at this time, chemistry was, let's say, or people lived closer to nature or probably had more the feeling of being embedded. And that's a feature of sustainable chemistry, that we have to learn again to embed industrial chemistry, to embed chemistry education more into the context, in our world nowadays, into the context of sustainability, where we also have things that are closely related to nature. If you think of the planetary boundaries, the limitations of resources, the effects of chemicals in the environment and humans. So in fact, all around us, where chemistry is embedded. In between, we have thought chemistry is above or independent of nature, of everything more or less, which is fostered by, I would say, the conventional chemistry education. You are in a lab, you are in an artificial situation, you are going for new compounds, which is at the heart of chemistry and is fine, but you do not yet think about how will this really work out. Or in other words, you get a textbook as a student, at least was my experience, and you go in the lab, you do your practical, and you think, yeah, that's it, that's how it works. You're not thinking about products, you're not thinking about industrial chemistry, and you are not aware that many of the things you are reading in your textbook is the result of a lot of, let's say, PhD students and other students, how to generate the insights. And we just are taking it or have taken it for granted.
And so how is research changing, or education changing then?
I think education has to change in terms of looking a little bit more beyond chemistry, for what, for whom. As long as it's a science and as long as you're really in the lab and doing experiments there, it's fine. Then it's, as you could say, it's non-normative, it's not depending on human value propositions. Chemistry or molecules and atoms do what they do under given conditions, and if you want to get insights, what they are doing, that's fine. But nowadays, students have to learn also about this embeddedness and think about what is the purpose. Or sometimes I'm asking students, you came up with a new reaction or new catalyst or new application. I wish you all the success to bring this into practice. But have you ever thought what this would mean if your product, if your process, if your reaction would be applied in a 1,000 or 100,000 scale of tonnage? What are the resources needed? What are the byproducts? For a long time we were only interested in yield. We were not interested in the waste we are generating, for example. And this already we have to take into account in teaching. By the way, waste is also a human concept. Nature does not tell us something about waste. Nature is just nature, and chemistry as a natural science is just chemistry first of all, but it's our human value propositions that we think waste is something we don't want to have, or waste should be avoided, maybe because it creates costs, maybe because it's toxic. But then again, it's our value if we say organisms in the environment should not be impacted, or toxicity is bad. Nature just sees, or sees inverted commas, that there's an effect, and maybe evolution will then find or come up with other organisms or whatsoever over time.
So we have to learn early on that we have the bigger picture in our view, or maybe this more systems thinking in education?
Yeah, systems thinking is a very important word. in education, but also in research, also in industrial chemistry when designing a new product where you often need several chemicals, for example, because it emphasizes there is more than just this punctual thinking. I'm now optimizing something from 95% with respect to 1, 2, or 3 properties. And I do not think, for example, how much resources will this cost, how much energy, or how much waste this will generate at the end of the life of the product. So we also have to think from the very beginning, before we even start the synthesis, if it's not just for curiousness, what will be the end of it? Will it end up in the environment, or will it be a product that can be circulated or should be circulated? Yeah, and according to this, starting from this, let's say, very end of the life cycle, going back to the beginning of the life cycle, we should think about which chemicals, which products, which materials we want to have and how to design them.
Can you give examples from your research for this?
Yeah, there are 2 foci of my research. One is typically in the lab, and the other is more on the conceptual level. In the lab, or in material-based research, you could say, we are focusing on the benign by design principle, which is one of the green chemistry principles. That means to render molecules degradable, in our case, in the environment. That's because I have a background of environmental chemistry, and for a long time I studied the presence and the risks of chemicals in the environment, but at some day I was a little bit bored by this. Wow. Measuring the 500th compound and the 700th sample and doing the 400th risk assessment, and nothing changes really. So I became interested in how can we change this? How can we, from the very beginning, avoid problems? I think that's at the heart of it. And if we are able to design chemicals, pharmaceuticals, in a manner that they are stable enough, the lifetime is long enough in the area where they are applied, but when they enter the environment, for example, the aquatic environment, that then are fast and completely degraded. Completely is also important because we have a lot of treatment processes, for example, on the one hand, which result in just transforming the parent molecule to follow-up products. And often we do not even know how toxic these are, what is the environmental fate. And also, if you think about only 20% of world's wastewater is treated. So we need a solution which works everywhere. And at this time, I also came across with green chemistry and the 10th principle and said, okay, it's written there, but there have been only a few very, how should I say, simple examples and not completely to the end and not completely shown that it works. Mm-hmm. And that's what we did in the meantime. So that was a journey of more or less 20 years, mm-hmm. To demonstrate it's feasible, including pharmaceuticals, which we could patent. Mm-hmm. That's important not because we will get rich, probably not, but it demonstrates to industry there's a new business opportunity if you have new compounds that are patented. And the core of this thinking is starting at the end of life, oh, this chemical will probably go to the environment. And then going back to the very first step, how should a chemical look like? Mm-hmm. And then thinking about which are the part of the molecule, the core structure, that is needed for a good performance in application. Mm-hmm. And then identifying moieties which can be changed and giving access to degradation, to complete degradation, mineralization in the environment. Mm. Chemists should think about kinetics, about half-life. How long is this compound stable under which conditions? That's a sort of a key of it, because conditions in the environment are different, pH, excess of light, excess of water, than in an application. And by the way, then after time we learned, going for circular economy, sometimes it might be helpful to have a very stable compound. If you think of solvents, if you can make sure that they do not go into the environment, make them as stable as possible. Mm-hmm. because then you can circulate, and that saves you energy and waste, because there's no need for new synthesis.
Can you give one success example?
We had several examples where we can demonstrate this. One is ionic liquids, yeah, which are more and more important, not only as green solvents, but also used for photovoltaics and other energy applications. And that's one example. We worked also on pharmaceuticals, and there we could even patent a new compound. Yeah, and we could show it's still active as it should be, as an antibiotic. It's stable enough in the human body, and as far as we could investigate, has less unwanted side effects than the compound it could substitute. And after its excretion, it falls apart in two pieces, and there's much more improved degradability in the environment. And to be honest, we are not yet there. There's one part which is still slowly degradable, but it's much less active than the parent compound. So in this case, we are also addressing the issue of reducing the probability that resistant bacteria are collected. So we are in two fields. We are in hygiene, antibacterial resistance, and environmental pollution. And both we could, with this approach, much reduce. And as for the time being, we're working on silicones, which is another challenging, very challenging task, but it's also very rewarding, because we learn a lot and have a lot, real fun in the working group and discussing with people.
And so when do you think will we see really cycles, circular economy cycles really working in the economy?
Many are already working. Yeah, if you think about glass, for example, others are just starting, where we have to improve the infrastructure. And as for more complex products, we have also to think about design. We have to design for recycling, or even if we go for plastics. So we have lots of polymer, a few basic polymers, but we have up to 10,000 additives. So we talk about plastics, but very often it's not just the polymer, or the polymer already includes different functionalities, different types of atoms. This we have to simplify, else it will never work. Yeah, and we have to depollute the products. If we have persistent and endocrine active flame retardants therein, it will never work. But also if this we have to move out, and but also if the compounds are not toxic, it's a mixture, and a mixture is always challenging to separate. Yeah, you can do it sometimes mechanically, but if the additives are in there, maybe you need chemistry, and each separation needs energy and results in waste. That's just because of thermodynamics. That's the message to my colleagues. Don't forget thermodynamics. Many of the students do not like it, but it's so simple. First law, you will never win, you can only break even. Second law, you can only break even under perfect conditions. Third law, sorry, you will never reach perfect conditions. And now look around our world. If everything would be perfect, there would not even be life. So we can't avoid, we can only try to lose as little as possible. And now coming back to benign by design, we also need to design complex products for recycling, for example. And we also researched on this. Now we are in the field of our conceptual work, because we are not material scientists, but from the basic principles of chemistry and physics, it's easy to derive. If we want to cope with unnecessary entropy, waste and energy losses, material losses, in circular economy, in circulation, we have to simplify things. We have, for example, on all level, maybe a lower diversity of different atoms, a lower diversity of molecules, maybe less branching, for example, less additives, or maybe even sometimes without, less different metals. And then we go to the next step, the building blocks. Also the same, less of them, maybe, and then thinking about which ones if I go for recycling, I need separation. First, we should go for circulation, but at the end of the day, we have to go to recycling. And the easier I can separate them, the better. So that could be one of the design principles we derived. And last but not least, we have to acknowledge circulation, circular economy is not sustainable per se. Not everything which is greener fits into a circular economy or is more sustainable. And not everything which is part of a circular economy and is made for it does mean that it's at the lowest amount of energy needed, it's at the lowest amount of toxicity, resources needed. But for example, all the waste, also recycling will create waste. And we have to think of this also. That's the challenge or the incentive of the future, to do more with less. And that's quite normal in science, for example. That's Occam's razor, that's a principle of scientific philosophy. Keep it as simple as possible.
And do you think this is a nice vision, or do you think this will really come true in maybe 5 years, 10 years?
I have to confess, I'm a bit biased. No, I'm really convinced, because we see the drivers are there, and we see it if you look to industry, if you look on our chemistry community, the pressure is felt. More and more people see resources are not endless. More and more people see, wow, despite all what we have done, this end of the pipe approaches we have done for 50 years, which have been in some respect quite successful, they are now coming to an end in terms of, yes, we have done a lot of, but they will not be able to solve the real basic problems that are arising from the huge amounts, tonnage we are using, and the high diversity we have there. And again, it's about, yes, we have to reduce what we are turning around of material in time, how fast, in space, and in diversity. Yeah.
So what inspired you to focus on sustainability in your research?
Oh, that's a very good question. I've taken it for long for granted. Yeah, it was not just one moment, but at the one hand, I'm very fond of chemistry. On the other hand, maybe typical German, Faust, I wanted to understand what keeps the world together. But then also I wanted to contribute something, yeah, and making best of chemistry. Yeah, I was, for years, I would not say depressed, but I found it such a pity that people do not appreciate chemistry and what's around us. So if I talk to laymen, I always ask, where's chemistry here in this room? Often there's silence. But in fact, everything is chemistry. Nowadays, most synthetic chemistry are the result of it, but also natural chemistry. Yeah, and therefore, I wanted also to contribute with environmental protection. So when I studied environmental chemistry, was not really there. But I went into this field, and first time I noticed people think we are a little bit crazy, that's not important, and we can manage this easily. And then after environmental chemistry was established, I saw it's not really solving the problems. It's an important tool to solve some problems and to gain knowledge, what are the problems, but not all of them. And then we had the discussion about resources, yeah, and the limitation. But that was very clear. If you look at the formula of a globe or of a ball, you see it's not endless. Yeah, and energy, it's the same. And that was the point, moving to the next step to say, how could solutions like positive things. I was also a little bit bored or fed up with that I also always have to come up with problems without having a solution. Yeah, and maybe another point is that, yes, I'm very interested in chemistry, but chemistry is only part of life and what we have around us. So life and what we have is much more. So I was interested in a lot of things, just for interest. And maybe that's also a message to the younger ones. In school, when you're studying, also to do some things that are outside of your interest. Sometimes you have to do things. I have a lot of examples in my life. Do I really have to do this? Why do I have to learn this or understand this? Later on, I thought, wow, very helpful. Yeah, or also being interested in culture and politics. Nowadays, we talk about resources, but resources is geopolitics. Without resources, you will not understand the Iraqi war, you will not understand the behavior of China, you will not understand Ukrainian war, etc., etc.
Yeah. So we're coming back to the larger picture and the system thinking. And do you have maybe one sentence tip for somebody, for a chemist? What can we do to, I don't know, change our mind that we think more of this larger picture of the systems thinking, more sustainable?
Be curious, and if something works, do not just stop. Think about why does it work and under which conditions and how this relates to reality. And what will be the result if you would be successful. And do not give up if everyone tells you that does not work. We have been told many times that does not work, and I ask people, where do you know from? Yeah, we just know. And I said, I am a scientist, I want to find out whether it really does not work or work. So stay curious.
Okay, thank you very much.
My pleasure.